going back to our pizza recipe, 1 crust, 5 ounces of tomato sauce, 2 cups of cheese, makes 1 pizza. What if we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce? How many pizzas could we make? I have a 4. Anybody else? 3? How are we thinking about that? Yeah, so there's 4 crusts, so we could make 4 pizzas from 4 crusts, right? But there's 15 ounces of tomato sauce, and how many pizzas can we make with that?
3.
Only 3. So could we make the 4th pizza? No, it wouldn't have any sauce, right? And then there's enough cheese to make 5 pizzas, but we don't have enough of the other things. So when you're cooking and you run out of ingredients, you have to stop making whatever it was that you're making, right? You can get creative and make something else maybe, but you can't make exactly the same thing when you run out of one ingredient. So again, with the pizzas, we can just kind of think about this, but let's look at how we would write this down using dimensional analysis so that we can apply the same idea to running out of one of the reactants in a chemical reaction. So what we're going to do is we're going to take each of the reactants or ingredients and we're going to find out how many pizzas we could make from that. Now we did this cheese one already. What this is saying is that there's 1 pizza for every 2 cups of cheese. 1 pizza for 2 cups of cheese. So that would be 10 pizzas. No. 5. Oofda. So with the crusts, we're also going to use a conversion factor from this recipe or this equation. Here it's 1 pizza for every 1 crust. 1 pizza per 1 crust. I didn't cancel those out. And so 4 crusts should give us 4 pizzas. And then for the sauce, we're going to look at, well, what's the relationship between pizzas and ounces of sauce? 1 pizza, 5 ounces. 1 pizza for 5 ounces. The ounces of sauce cancel out, and we get 3 pizzas. Yeah, thank you. Brain fart. There's been a lot of that happening today. 4, 15, 10. Okay. Thank you for catching that. So the idea here is that we took each of the ingredients and separately figured out how much of the product we could make using that ingredient. And then what we do is we look at the amount of product and we're going to choose the smallest one. Because when we get to 3 pizzas, all the sauce is used up. So the cooking of pizzas cannot continue because there's no more sauce. It just is going to stop. And in a chemical reaction, when you run out of one of the ingredients, one of the reactants, the reaction stops. And so here it is with pictures. So the 4 crusts would make 4 pizzas, 10 cups of cheese would make 5, 15 ounces of sauce would make 3. And so this amount of sauce limits the amount of product we can make. So this is called the limiting reactant. And the amount of product is going to be whatever is the smallest of those. So we call the tomato sauce a limiting reactant. And the maximum number of pizzas we can make is called the theoretical yield. So if we go back to that picture, this is theoretically the most pizzas we could make. Could something happen where we ended up with fewer than 3 pizzas? You ever have disasters in the kitchen? I have a puppy at home. All kinds of things have been happening, right? So, what we'll talk about in a minute is that there's also an actual yield. Like, maybe you were trying to be fancy and spin the crust and stuff and it fell on the floor, right? So there goes one of the pizzas and you only have 2. So in a chemical reaction where we have more than one reactant, it's very likely that one of the reactants will be used up before the others. Just like when you're cooking, you're usually going to run out of one thing. It's never going to come out even, right? You're baking cookies and you run out of eggs or you run out of flour. You don't run out of everything at the same time. And that's how it is in most chemical reactions. So that reactant that stops the product is called the limiting reactant. The limiting reactant gets completely used up. And the other reactants that do not get completely used up are said to be in excess. There's extra left over, right? When we're done making that pizza, we've got some cheese left over and a crust. That's probably why they started making cheesy bread, because, I have to use this stuff up, right? But it's not pizza. So the actual yield is how much is actually produced. So you drop a pizza, you burn one, something happens. So you should have been able to make 3 pizzas, but you actually only made 2. So that's your actual yield, and we express the efficiency of the reaction or of making pizzas by what's called percent yield. So this is the equation for percent yield. It's the actual yield divided by the theoretical yield times 100. So if we made 3 pizzas like we were supposed to, we'd have 100% yield, 100% efficiency. It'd be perfect. Right? If we end up with 2 pizzas, then that'll be 2 pizzas divided by possible 3. So that's going to be 67%. Any questions? So this is just a summary slide that sort of defines all these terms. I'm not going to read it to you because... So let's go back to the combustion of methane. So this was our chemical equation, and we had our little models here illustrating what was happening. So the equation is indicating that 1 molecule of CH4 is going to react with 2 molecules of oxygen. Well, what if we have 5 molecules of methane and 8 molecules of oxygen? What's going to happen? Here we're interested in the CO2 that's being made, just because that's what they said we're interested in. Well, we'll take the one ingredient, the 5 molecules of methane, and we'll look at the coefficients in the balanced chemical equation, and we'll convert amount of methane to amount of carbon dioxide, and we get 5. It's just like the pizza crusts, right? It was 1 for 1. And then we can look at the other reactant. Here we've got 8 molecules of oxygen, and from the balanced chemical equation, we see that we get 1 carbon dioxide molecule for every 2 molecules of oxygen. So this is only going to yield 4 molecules of CO2. So we're going to hit 4 molecules of CO2, and like when we hit the 3 pizzas, it has to stop because you ran out of an ingredient. Does that make sense? Once all of these get used up, then we're done. Do I want to try to draw that? I'm going to try. It just occurred to me that this would be kind of cool. So we're going to call those methane molecules. They kind of look like weird daisies, but and we had 5 of those, right? Note to self for the future, take a screenshot and crop it so that you can paste it in here and look all fancy. Maybe. So here's the 5 methane molecules and the 8 oxygens. What would be a good color here? Orange, maybe? So we could have these 2 oxygens react with that methane. And we could have these 2 over here react with this one. And these 2 react with that one. And those 2 react with that one. So what happens? We've got a methane molecule left over. So we're going to make these 4 carbon dioxide molecules, 1, 2, 3, 4, 1, 2, 3, 4. But then there's going to be a methane molecule left over. Okay. Sometimes students will do the calculations all beautifully and they'll say, I can make 5. Well, no, you can't because you run out of the oxygen. You can't make any more. And you definitely can't make 5 plus 4, 9, right? Just like with the pizzas, we couldn't make 3 plus 4 plus 5 pizzas. It's kind of silly, right? But it doesn't seem so silly when you're talking about chemicals. Does anybody have any questions? Is this making some sense? Yeah.
So we're supposed to find the amount of moles to the other moles of the molecule in the chemical reaction?
Yeah. Yeah, so the conversion factor here comes from the chemical equation. And so this is showing me that I need 2 molecules of oxygen for every 1 molecule of methane. And that's where you'll always find that relationship. So here's another question. So nitrogen and hydrogen form ammonia according to this reaction. A flask contains a mixture of reactants represented by the image shown at the left. Which of the following images best represents the mixture in the flask after the reactants have reacted as completely as possible? And what is the limiting reactant and which one is in excess? So you can do this kind of like I did with my ugly drawing there, and you can kind of group these things, right? For every 1 nitrogen, you need 3 hydrogen molecules, right? So here would be 1 nitrogen with 3 hydrogens. Those could combine to make 2. They would make 2 ammonia molecules. And then I've got another nitrogen here, and it could react with 3. And so that's going to make 2 ammonias. Well, that's not right. And this one's going to make 2 ammonias. And then what's going to get left over? These 2 hydrogen molecules, right? Because there wasn't enough nitrogen for them to react. So which of these flasks best represents what we have at the end? C. Because here we have 4 ammonia molecules and 2 oxygens left over. So what is the limiting reactant? It's the one that gets used up, the nitrogen. Right, so nitrogen is the limiting reactant, and which one is in excess? The hydrogen. okay? There's some hydrogen left over, there's extra, there's excess, more than needed. Any questions? Okay, so on Monday, we learned how to do grams to moles to moles to grams, right? So if we're looking at amounts of product, we're often looking at those in terms of grams, right? And we're looking at our starting masses or amounts of reactants in grams. So this is what your book suggests that you do, and there's nothing wrong with it. They say for each of them, calculate the moles of product, choose the smallest, and then convert that to grams. So what I like to do is let's just take this to grams and do this one to grams. And just choose the smallest one, and that's the answer. So we're going to do that stoichiometry calculation twice. Grams to moles to moles to grams, and grams to moles to moles to grams. And whichever one gives us the smaller amount of product, that's the one that tells us how much we could make, because that reactant is getting used up. So here's a real chemical problem. Reaction mixture contains 42.5 grams of magnesium and 33.8 grams of oxygen. What is the limiting reactant and theoretical yield? Suppose that the actual yield is 55.9 grams. What is the percent yield? Okay, we just jumping in with both feet, and we're going to do all the things. So we're given some information, a mass of magnesium and a mass of oxygen, and we're told that this is the actual yield. And then they're asking for the limiting reactant, the theoretical yield, and the percent yield. But we need to do these just one thing at a time. So like I did before, I'm going to use this mass, and I'm going to write it under the symbol or the formula. So we've got 42.5 grams of that and 33.8 grams of this. And so they're asking us for the limiting reactant, but they're also asking for the theoretical yield. How much product could we make? So what we're looking for is how many grams of this. This is different than what we did on Monday, because now both of these reactants have masses. That's because this is a limiting reactant problem. When they both have masses, that means you do the calculation twice. If there was 3 or 4 or 5, you have to do it 3 or 4 or 5 times. But it's always 2. So we're just going to do grams to moles to moles to grams for both of them, and then pick the smaller one, and that's our theoretical yield. So grams to moles to grams. So I'll do the first one, 42.5 grams of magnesium, and we're going to moles of magnesium, and then moles of what? MgO, yeah. Sometimes you're like, oh wait, should I go to oxygen? No, this is the thing we want to know, the amount of product, okay? So we're going to take both of these to magnesium oxide, and then to grams of magnesium oxide. So I've got grams of magnesium down here. This is dimensional analysis. Again, or still, depending on your point of view. Use it a lot. all the units in first. Then put the numbers in. This is a mole ratio. It's a ratio of moles. This comes from the coefficients in the equation. This is 2 moles of magnesium and 2 moles of magnesium oxide. So 2 moles of magnesium, 2 moles of magnesium oxide. Converting between grams and moles, we need a molar mass, right? So for magnesium, we just have to look at the periodic table. 24.31. Yeah. And then for magnesium oxide, we're going to have to calculate that, right? So that's 1 magnesium plus 1 oxygen. I'm sorry, 40.31. So 40.31. So the answer to this part is 42.5 divided by 24.31 times 2 divided by 2 times 40.31. Our starting number had 3 significant figures. So our final answer should have 3 significant figures. I'm keeping some extras here. Now we're going to do it again. It's extremely similar, not exactly the same, but very similar with the other reactant. So we have 33.8 grams of oxygen. Grams to moles to moles to grams. Now go to moles of O2 and moles of MgO, and then grams of MgO. You're always going to find the same substance when you're doing limiting reactant problems. Come on. So the grams cancel out, the moles of oxygen cancel out, and the moles of MgO cancel out. What should I write in front of moles of MgO? 2. Because there's a 2 in front of MgO. What should I write in front of moles of O2? 1 or nothing, right? It's not a 0. That's a 1 that we didn't write. Most people prefer to have numbers in there, so that's fine. Here's oxygen. We need its molar mass. That's 2 times 16. It's 32. This last term is exactly the same. We don't need to recalculate the molar mass. It's just going to be the same. So 40.31. 33.8 divided by 32 times 2 times 40.31. And this is giving me 85.154 grams. So I have 2 answers. Which is the answer to what is the theoretical yield? The smallest one. So this is the smallest one. That means when we make 70.472 grams of this product, the reaction is going to stop because we've run out of what? Yeah, we ran out of magnesium. So this is the smaller one. And so answering the question, what is the theoretical yield? It would be 70.5 grams. So I call him Ty. And this is lure limiting reactant. We're not going to use that other equation at all. Well, why did we have to write it? Because we didn't know which one was going to give us the smaller answer. We're not quite done yet, but any questions? So we've got our theoretical yield and our limiting reactant. That's the magnesium. We need to calculate the percent yield. So let's do that up here. Oh, let's just stick with the red. So percent yield is how much you actually made divided by how much you theoretically could make. So I get technically this is yield. Theoretical yield times 100. This is our theoretical yield. Best to use the unrounded number in the calculation, 70.472 grams. What's my actual yield? 55.9. If this was an experiment we were doing, and like with our copper, collect the copper and you weigh it at the end, that's your actual yield. That's how much you actually got back. But if we're not doing the experiment, then they have to tell us that somewhere in the problem. So 55.9 divided by 70.472 times 100 is going to give me 79.3%. Any questions? Now, whether that is considered a good yield or not depends on a lot of things. So, magnesium is the limiting reactant, 70.5 is the theoretical yield, and this is the percent yield. Let's do another one. Ammonia can be synthesized by the reaction 3H2 plus N2 goes to 2NH3. What is the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of H2 and 31.5 kilograms of N2? So again, I'm identifying what kind of numbers are they giving me. I'm identifying what are they asking, theoretical yield of ammonia. And then I'm going to take my numbers and write them under the chemical equation. So 5.22 kilograms and 31.5 kilograms. Always a good idea to just, take a second to double check and make sure you didn't switch them. And then the theoretical yield, we're trying to find how many kilograms of ammonia we can find. So we're going to do stoichiometry. What's the path? Grams to moles to moles to grams. And we have two masses given, so how many equations do we need to do? Two. We need to do the calculation twice. So this is another one of those with the kilogram at the beginning and at the end. So I believe on Monday, I did it where we just wrote the whole thing out. And we saw that the conversion between kilograms and grams at each end canceled each other out, right? So I'm going to show you a different way of thinking of that so that we don't have to write everything down. So I'm going to do the first reactant first because that's how my brain works. 5.22, I'm going to write kilo in red. Because kilogram means 10 to the third times grams, right? And so what we're going to do is we're just going to let the kilo sit there. We're not going to cancel it out. We're just going to cancel out the grams. And then at the end, we can push it back with the gram that we get there, and we'll have our correct unit. So that is kilograms of H2. And I'm going to moles of H2. And I'm going to moles of NH3. And I'm going to grams of NH3. So we take those previous units, and we bring them down. And here, the grams H2 is canceling the grams H2, but not the kilo part. What's the mole ratio here? What goes in front of H2? 3, and in front of NH3? 2. We need the molar mass of H2. So 2.016. And we need the molar mass of ammonia. And then we can calculate the answer. So 5.22 divided by 2.016 times 2 divided by 3 times 17.034 equals 29.404. And I have gram as a unit that's left, and kilo that's not canceled out. So my unit here is kilogram. Do you like that way of just setting the K aside, or do you like the other way? Not sure? It's shorter. Mm-hmm.
But it's just not something I'm used to, so I like everything written out
Yeah.
until I get comfortable.
Right. When you're first learning, it definitely is helpful to many students to just write everything out, even if it takes longer, because you do it correctly and you get the right answer. And after writing everything out for a while, then you start to be able to take some shortcuts. So I'm going to show you something that's kind of in between this one and the other one. So this is the shortest one, and the one we did last time was the longest one. So this one will be in between. I'm just going to switch to green because there's so much blue here. So 31.5 kilograms of nitrogen. What does kilo stand for? 10 to the 3. So I could write 31.5 times 10 to the 3 grams of nitrogen. This is what I'm writing instead of kilo. K and times 10 to the 3 mean the same thing. You can just switch them out back and forth. Okay? So that way we're going to skip that step at the beginning. We're kind of doing a little hack of converting to grams without seeming to convert to grams. So grams of nitrogen to moles of nitrogen to moles of ammonia to grams of ammonia. And then I'm going to have these units cancel out. kilograms nitrogen. Again, the mole ratios come from the balanced chemical equation. 2 moles of ammonia, so there's a 2 in front of NH3. And 1 mole of nitrogen, so there's a 1 in front of nitrogen. The molar mass of ammonia has not changed in the last few minutes, so that's still 17.034. And then this one is 2 times the mass of nitrogen, which would be 28.02. So this is going to get us to grams. And then once they convert to kilograms, right? So kilogram here, gram on the bottom. Kilo stands for 10 to the 3. 1 kilogram is 1 times 10 to the 3 grams. And there's the grams canceling out. Zoom out so I can see the whole thing. Okay, so 31.5 EE3. That's not proper scientific notation, but your calculator doesn't care. Divide by 28.02 times 2 times 17.034. And then I'm going to divide by 10 to the 3. So this is going to give me 38.299 kilograms. So what is our theoretical yield? Which is smaller, 29 or 38? 29 is smaller. So this is our theoretical yield, and so we're going to say the theoretical yield equals 29.4 kilograms of ammonia. Any questions? There's another one. Need a lot of practice with this. Mining companies use this reaction to obtain iron from iron ore. The reaction of 167 grams of Fe2O3 with 85.8 grams of CO produces 72.3 grams Fe. Determine the limiting reactant, theoretical yield, and percent yield. This is another big one. So many questions. So we have 3 numbers given to us, and then they're asking us for 3 things: the limiting reactant, the theoretical yield, and the percent yield. – 167 grams of Fe2O3, 85.8 grams of CO, and then they're telling me 72.3 grams of iron. So to calculate the theoretical yield, we're supposed to do 2 calculations, one with this reactant and one with that reactant, to find out the amount of product that's made, but we already have a number there. What's going on? This number that they gave us is the actual yield. They're not calling it the actual yield like they did in that other problem. They're saying this reaction produces 72.3 grams. So we have to recognize that that is the actual yield and pull that away and say this is the actual yield. The theoretical yield is the amount of grams of iron that we get from our calculations. So 2 calculations again. Grams to moles to moles to grams. 167 grams Fe2O3. I'm going to moles. of Fe2O3. And then I'm going to moles of iron, and then 2 grams of iron. In this problem, there are 2 products being formed. How do we know that we want to calculate the mass of iron? Well, the sentence tells us we're talking about obtaining iron from iron ore. So the point of doing this reaction is to get the iron. And then here, they're giving us an amount of iron. And so we need the mass of iron that theoretically could be produced. So grams of Fe2O3 and moles of Fe2O3 and moles of Fe. There's 1 mole of Fe2O3 for every 2 moles of iron. 1 mole of Fe2O3 for every 2 moles of iron. Molar mass of iron is 55.85 grams. And then we have to calculate for the Fe2O3. 2 times 55.85 plus 3 times 16. 159.68. 167 divided by 159.68 times 2 times 55.85. $116.82 grams of iron. Choo-choo to you too. So then we're going to do the other one. 85.8 grams of CO. Grams to moles. To moles. To grams. And then we put the units in. I didn't cancel the ones up there, but they all cancel so that our units cancel out. This is going to bother somebody, so I'll fix that. Cancel those guys. The one at the end is going to be the same. 55.85. In the middle, we've got the mole ratio, 3 moles of CO, 2 moles of iron. 2 moles of iron, 3 moles of CO. And then we need the molar mass of carbon monoxide, which is the mass of carbon plus the mass of oxygen, which is 28.01. So 85.8 divided by 28.01 times 2 divided by 3 times 55.85 equals 114.05 grams of iron. What is our theoretical yield? The smaller one, right? It's the 114. Because when you get to 114.05 grams of iron, you have run out of this guy over here. Did I do that right? Anybody else check my math? I thought it was the other way around. Let's peek. No, that's what it is. colors. Green maybe. So this is my theoretical yield, 114 grams of iron. And the reactant that gave me the smallest answer is my limiting reactant. So it's asking for the limiting reactant, that's carbon monoxide, the theoretical yield, 114 grams. And now we need to calculate the percent yield. So the percent yield is the actual yield, which they gave to us. They didn't flat out tell us it was the average yield, but they gave it to us. It's unpleasant. Any questions?
So if it's only asking for, what do we do with the 3 CO2? We just leave it be, or is that? I don't know.
Well, we're using this 3.
Okay.
Oh, you mean that
Yes,
guy?
Yes.
That's the other product, and apparently we just don't care about that one in this problem.
Okay. So unless it's asking for it.
Yeah.
Don't overfill.
Yeah, if there's more than one product, they're going to ask you about one of the products. They're never going to make you calculate both of them. With this last conversion factor being exactly the same for both of the calculations, this is why I don't see the point in stopping here to find out the moles that are smaller and then multiplying by that. It's only a tiny bit of extra work to just do it for both of them, and then all you have to do at the end is circle the smaller number, and that's your answer.